Ladies and gentlemen, welcome everyone. I am Dr. Roland A. Drolet, PhD in Biomedical Engineering from the University of Toronto, 1971. I am the developer and inventor of the RUMART PEM system that has helped over 1 million people all over the world who were suffering from all kinds of health problems. Today I'm with my son, François Drolet, gold medalist, Olympic gold medalist in Nagano, Japan, in short track speed skating. I'm going to say a few words about the elasticity and what we call Young's modulus. Young's modulus is a measure of the force per surface area necessary to break something. Let's say this would be a steel rod, for instance, of radius r. So the cross section would be pi r squared. Okay? So the force necessary to elongate this, to break it, to destroy atomic bonds, which are very strong. Okay? We call the ratio of the force necessary to break it, to elongate it, per area, the Young's modulus, okay, in the name of the first measure. So we have the elastic law is the force equal time constant that we call in our case atomic spring, because we are talking a lot about atoms. So you could think this of two atoms that you want to separate in a molecule. So you could think that it takes a certain force. If you elongate it to a certain distance, it will break apart. Okay? So same thing, same type of concept applies to atom as it applies to a whole piece of metal like this. Okay? And when you divide the force by the surface, you can calculate how many atoms there are there. So you can calculate the necessary force there, like the Young's modulus is in the range of 10 to the power 11 Newton per meter for steel. So it's a lot. It's 100 billion Newton per square meter. And dividing by the number of atom in this cross-section bar, you can calculate the force it takes to separate two atoms there. But of course it's not only two atoms, because there are many of them. So it's one layer from the other layer. So you could imagine by dividing by the number of atoms what it would take for one. Okay? Okay, so this is about it. Now in some of the equation, when we calculate the Einstein frequency, for instance, it's 1 over 2 pi, because 2 pi f is the angular frequency, we call. But Einstein frequency is like the atomic spring constant, like in here, for an atom, divided by the mass of the atom. So in this way, Einstein calculated, he looked at atoms as they would be little springs together, you know, and calculate, for instance, what is the actual energy of excitation when you increase the temperature of metal so that the bond breaks and it becomes a liquid. So it is when the atoms in the metal vibrate too much, if you increase the temperature, it dilates. And if you increase too much the temperature, atoms are vibrating so much that it breaks away. Okay? That's when a solid becomes a liquid. And for a liquid to become a gas in the air, it takes a lot of energy. Why? Because you need all the energy for the atoms to get lifted up in the air. So they need a certain speed. So this is why from a liquid to a gas, like when you boil water, water is the easiest because smallest molecule. But when you heat it up at certain time, even in a liquid, molecules vibrate so much that they get the hell out of there.
Yeah.
That's it. And with the electrical equation we've seen. So that's the basic idea of elasticity of a spring. And we can apply this concept to the elasticity of the electromagnetic medium.
Okay.
So as we will see in some other clips. So here I just want to mention a few things about ionization potential. See, because here I talk about classical mechanics and I touch some subject of atomic physics. Because when you get to the level of atoms and molecules, then it's really quantum mechanics that applies to understand how things behave there.
Okay.
But now it's just a try to calculate the ionization potential of hydrogen atom, okay? Knowing that electron, say in the Bohr model of atom, the electron can circulate on certain orbits. They cannot be everywhere.
Okay.
This is what we call the n orbit. Okay. So actually, we know that the escape velocity, for instance, of a satellite from the Earth is the square root of the velocity to go around it in a circular motion. If you increase the velocity by a factor square root of 2, it will get off. So that's what we have to do when we send a satellite in orbit. We have to increase its velocity to 1.4142. If you get this, it goes out, and then it would be catched by the sun or another planet. Okay, and so just applying these Newton laws of mechanics to an atom, and just see if we are in the same type of range. So I just asked myself, well, we know the velocity of the electron on the first orbit of the atom. It's about 137th the speed of light. It's real fast. The speed of light being about 300,000 kilometers per second. It takes a second to go to the moon. So the speed of the electron around the proton in an hydrogen atom goes at about 100th of the speed of light, which is real fast. And we know that if it would go square root of 2 faster than the speed, it would get the hell out of there. Okay, according to classical mechanics. Just equating the electrical force attracting the electron and the proton, because gravitational force between the two is negligible, about 10 to the power 32 larger electric force than gravitational force. The force of attraction, gravitational is almost nothing there.
Okay.
But centrifugal force is not to be neglected. So when you equate the electrical force to the centrifugal force, you get, and you use the wavelength, which is a multiple of the length there. You consider the electron as a wave, okay? And if it cannot be in between. So if it has a certain wavelength, the electron, and if you gave it energy, it can jump on another state, level, but it cannot be in between, except going to the other plane.
Okay.
So that's interesting. So now I just calculated that the energy with this velocity, okay, where it would get away, minus the kinetic energy when it's on the first orbit, and this is the ionization potential where the electron gets out of that. Okay? So this is simply the kinetic energy, see, mass v squared divided by 2, with the n1 and n1 escape from n1 minus velocity on n1. This you equal just to the charge of the electron multiplied by potential, because the energy of a charge is the charge multiplied by the electrical potential. So if you equate this, you can calculate the ionization potential just from classical mechanics. And you end up with not the exact answer, because electrons are much more complicated than just a little mass. It has a spin, it has angular momentum, and it is what we call a spinor in quantum mechanics. But nevertheless, we get the same, the good range. Like the ionization potential of hydrogen, if I remember well, it's around 13 or 14 electron volts. There we get 21, okay? But this is because of the atomic aspect of this. So is that clear enough for you?
Yeah, yeah.
Okay, so this is just really showing that the concept of classical mechanics can be used to try to understand atom, and it doesn't give the right answer. So that's why we had to invent, physicists had to discover quantum mechanics and go much further. Okay. Even the orbit of Mercury around the Sun is much smaller than the Earth, and it's much closer. So before quantum mechanics, the Newton mechanics, classical mechanics, could explain the orbits of all other planets quite accurately, either circular or elliptic. In general, it's elliptic. But Mercury was just not there. And it's only applying general relativity of Einstein that we understood that it was a confirmation of Einstein's general relativity to calculate the way Mercury behaves close to the Sun. It doesn't have a perfect elliptical orbit.
And why is that?
Because of the large mass of the Sun and the fact that the Sun is turning, it's twisting the space. And this is, like in quantum mechanics, the vacuum is considered, the space is considered like an elastic membrane, okay? And a very large mass deform the space. And space and time become stick together, okay? So that's interesting. So that's about it, I think, for this explanation. And I hope you enjoyed it. And thank you very much for listening.
Thank you.
Thank you.